Hello everyone, I'll be discussing one of our research entitled Importance of Extracted Features Using Thermal Imaging Technique of Photovoltaic Module. Our presentation is composed of the following: Introduction, Photovoltaic Cell and its Problem, the Thermal Imaging Technique, Feature Extraction using Histogram and CDF, our proposed algorithm, results and discussion, and conclusion. Renewable energy aims to be a reliable power supply, to maintain energy security, and to minimize the fuel spill and its demand. Therefore, solar energy as a renewable power source is needed. The following are the applications of solar energy. So for architecture and urban planning, for agriculture, heating, cooling, and ventilation, especially for seasonal weather, cooking, fuel production, electricity generation. The solar energy can be used to generate electricity in two ways. First, thermal solar energy using the solar energy for heating fluids, which can be used as heat source or to run turbines to generate electricity. The other one, photovoltaic solar energy using solar energy for direct generation of electricity using photovoltaic phenomenon. In the figure given, the sun reflects energy to the solar panel. The solar panel or the solar cell absorb incoming energy from the sun, and the electrons begin to flow and generate electrical current. The wiring connection to the household or the application captures the electrical current and combines it with power from other solar cell. Solar panel is responsible for collecting solar radiation, and it transforms it into electrical energy. There are factors affecting the performance of the solar panel modules. First, what type of particular material and components used. It depends on what particular specification of a solar panel. Resistance of the load or the IV curve, intensity of sunlight, environmental condition and shadowing, so it depends on particular location where the solar panel is located, temperature of the solar panel, and many others. Any imperfection in solar cells such as cracks, poorly soldered joints, and mismatches lead to increased resistance, which eventually become hotspot. The long-term effect of hotspot include burn marks that degrade solar cell and the photovoltaic backsheet, and which may eventually lead to fires if left unchecked. The most common solar panel defect is that of the broken or chipped solar cell, as shown in Figure 1, letter A. This problem is typically a sign of poor power production, which reduces the energy production of solar module. A low-quality manufacturing system may accidentally incorporate cracked solar cell into solar panels. Moreover, scratches are solar panel defects too, as shown in Figure 1, letter B. They may hold dirt and moisture which can penetrate the cause damage to the cells. The scratches in encapsulation seems to have a minimal effect on the solar cell, but they minimize the power production of the solar panel. Hotspot occurrences should be avoided in any photovoltaic installation of solar cell. As shown in Figure 1, letter C, the enormous power dissipation occurring in a small area results in localized hotspot, which in turn lead to destructive effects such as cell or glass cracking, solder melting, or degradation of the solar cell itself. Lastly, microcracks also have the potential to produce hotspot. Microcracks occur when the internal resistance of the damaged cell arises, causing an increase in the cell temperature as the current passes through, as shown in Figure 1, letter D. Thermal imaging as a solution is a special type of visual information that converts thermal radiation into the visual range perceived by the human eye. If thermal imaging techniques are to be utilized in the field of photovoltaic, the early detection of defects will be manageable. This could also help to provide important solar cell panel information such as characteristic, its health condition, and can be an assessment for power output estimation. Solar cell image extraction. Extracting the features of the sample thermal images of the solar panel provides more detailed information in contrast to an image in the RGB or red, green, and blue color model. And also, it provides essential information for fault diagnosis of solar panels. In this proposed research work, the image feature extraction that we use are histogram and CDF or cumulative distribution function. Histogram is an important tool for inspecting images which provide to view the spot background and gray value range at a glance of an image, while the CDF or cumulative distribution function provides the associated information of an image based on symmetric distribution of image grayscale value. The target should be linear CDF, which is associated to a uniform histogram. Below are the corresponding images for histogram and CDF. Thermal imaging technique is a special type of visual information that converts thermal radiation into the visual range perceived by the human eye. In Figure 2, shows the thermal imaging process. The infrared energy is emitted proportionally to the object, for example, the solar panel. This infrared energy from the solar panel is focused by an optical lens onto an infrared detector. The information is then passed to sensor electronics for image processing, which translate the infrared image or video detector output into an image or video that can be viewed on a thermal image display. Figure 3 shows our proposed methodology. The raw thermal solar cell images are loaded. It will be pre-processed to minimize the noise. Sizes are adjusted for statistical uniformity. Images will be processed for grayscale and histogram equalization to have a better input and better interpretation. Image enhancement technique such as the adaptive histogram and grayscale threshold aims to have a linear cumulative distributed function of the associated image. Image will be evaluated and assessed. Figure 4 shows all the acquired thermal solar cell images were segmented into solar cell sizes to provide a more detailed feature extraction. The pre-processing technique, all segmented thermal solar cell images were pre-processed. It aims to improve the raw image data that were suppressed by unwanted distortion or noise of some image feature. Sizes are adjusted to maintain uniformity and execution of statistical measurement. Figure 5 shows images taken using RGB camera and a thermal camera. The image histogram was plotted using the pixel values versus number of pixels. The histogram of the RGB solar cell image exhibits a good bimodal distribution. One peak representation, the object pixel, while the other peak representation, the background. This is good for selecting the threshold of an image. Conversely, the histogram of the thermal solar cell image shows a good distribution of pixels over the entire intensity range. The histogram also shows most of the pixel value to be clustered in a small area, whereas the top half of the intensity value are occupied by only a few pixels. The more pixels are eventually distributed over the entire intensity range, the easier the image can be transformed. Thus, a plot output is obtained. The CDF is more linear in thermal solar cell image. This means that a more enhanced image is produced. Consequently, the representation of thermal image in a different domain to extracted the features such as histogram and CDF is helpful for post-pre-processing, such as a pattern selection that can be used for classifying and assessing an image. Figure 6 shows the histogram equalization and adaptive histogram equalization for both RGB and thermal solar cell images. It can be seen that the image produced using histogram equalization contains a region that is significantly lighter or darker, the contrast of which is not sufficiently enhanced, and only works well the distribution of pixel values is similar throughout the image. Adaptive histogram equalization improves the image by transforming each pixel with a transformation function derived from a neighborhood region. Figure 7 shows the histogram equalization of both the RGB and thermal images, which exhibit widespread value of pixel intensity. The RGB histogram has more spikes and is less flat than the thermal histogram. By performing adaptive histogram equalization on both images, it can be seen that the adaptive histogram equalization of thermal image is flatter and contains many more features than of the adaptive histogram of the RGB image. Figure 8 shows the CDF representation of both the histogram and adaptive histogram equalization. It shows that the histogram equalization of both images, the RGB and the thermal image, it can be seen that the grayscale has been normalized. The thermal image provides a more linear CDF, and its ranges has been extended to occupy the entire spectrum of levels. To verify the importance of extracting the features from the thermal images, Figure 9 shows a portion of the 4 different solar panel images under 4 different conditions. All 4 images were extracted to determine the difference in their features in terms of the histogram and CDF. As shown in Figure 10, the 3 histogram result of the RGB image have more spike and less flat than the rest of the histogram. The histogram of non-defective image in the first image of the RGB indicates both the histogram equalization and adaptive histogram equalization exhibit a flatter and better distribution pixel intensity value. The histogram scenario for both defective portion of the solar cell panel exhibited almost identical result. The histogram under adaptive histogram equalization did not flatten and were not well distributed compared with the non-defective thermal solar panel. Lastly, the histogram comparison shows that the adaptive histogram equalization can be used to improve the contrast of the image. Figure 11 shows the CDF comparison of the 4 images. It indicates that the thermal imaging technique provides a more linear CDF compared to the RGB image. Moreover, the CDF under the grayscale of both defective solar panel is not at all similar to a non-defective sample. This paper presents an algorithm for thermal imaging technology that extracts the feature of thermal images, in particular, for solar panel applications, with the aim of simplifying the representation into an easier domain for analysis. Aside from image histogram, the CDF provides significant insight as one of the parameters when dealing with image processing. The experimental results reveals that the extracted results of thermal images provide better histogram and CDF features. Even if the RGB images were processed to grayscale and had histogram equalization and adaptive histogram techniques applied, implementing histogram equalization on the dataset provides increase in contrast and highlighted the elements of the thermal image. Adaptive histogram equalization improved the contrast of the image, and this could be observed in the corresponding histogram and CDF of the processed thermal image. The different resulting features of the thermal images could contribute to neural network in classification application, which could promote the development of different thermal image application. For example, such as non-physical feature recognition or prediction of solar power generation. These are the references that we use for this presentation. Thank you very much for listening.